constant is capital M is here. Okay. And at the same time, norm x at 1, students, norm x at 1 less than or equal to m into norm x, for all x being the capital N representation. So here, let T be a linear transformation from n into n dash. So how to derive the any two norms are equivalent? Prove that any two norms are equivalent means you must present the proof here. Okay. Now that is just you have to 4.3.7 theorem is here. Already we have explained here. Okay. There is no doubt. And according to this one, continuity of linear maps. Now this just you have to see here. Linear transformation is continuous. So that's why you are taking any two norms are equivalent. Any one of the positive real constant is capital M such that norm x at 1 less than or equal to m into norm x for all x belongs to capital N is here. Let T be a linear transformation from n into n dash. So that is norm Tx equal to norm of T of summation alpha I xi. Here I varies from 1 to n representations. Now enter that linear combination can also be written as norm of summation alpha I and Txi. So here alpha be the scalar elements. So that is the field elements. That's why mod alpha into summation Txi. So norm x at 1 into maximum of because all the values you are taking at the outside. See, this is alpha. Students, listen carefully. Summation mod alpha I, that value is an equivalent to summation mod alpha I. That value is an equivalent to norm alpha 1. So please rectify this mistake. This is alpha. This is not x. Please rectify this mistake. See in your textbooks. Okay. In this theorem, particularly summation is also connecting with absolute of scalar values and norm of the transformation values. So at on the first norm of is there. So summation mod alpha means mod alpha 1, mod alpha 2, mod alpha 3. So enter that value is norm alpha 1, norm alpha I. So this is maximum of norm Tx1, norm Tx2, so on norm Txn. So that is capital M into, say this is, enter these values are norm x at 1 values. So capital M into norm x, maximum of norm Tx1, norm Tx2, so on norm Txn is here. So finally, enter these values here m into maximum of norm Tx1, norm Tx2, so on norm Txn. That value is an equivalent to k. So this is the entire, this expression can also be written as k into norm x. So finally, norm Tx less than or equal to k into norm x for all x belongs to n. Capital T is bounded, hence then it is continuous. Okay, students, this is one of the important theorem. Since all norms on a finite dimensional linear spaces are equivalent. Okay, now this theorem is very important because all norms on a finite dimensional linear space, FDLS. FDLS means finite dimensional linear space, or VS means vector space. So you are taking any two norms are equivalent. Now you must applying in the given this theorem 4.4.2. Just you have to see and verify this theorem. So this theorem already proved here. Okay. So that's according to this one. Every linear transformation is continuous. Every linear transformation is continuous with respect to all the norms on the finite dimensional linear space. Okay, students. Now, suppose in examination, you must applying in the above theorem, prove that every linear transformation is continuous with respect to all the norms on the finite dimensional linear space means you must applying giving this proof. That is 4.4.2. Simply stated as prove that every linear transformation of n into n dash is continuous. Continuous means before all that a continuous function is bounded here. There is no doubt. But converse is not true because sometimes a bounded function is not continuous. There are so many examples. We have practiced some other problems in under UG level. Under of course, under UG level is there. That is the real analysis. Okay, limits and continuity problems. Okay, Now the one of the properties, every continuous function is bounded, but bounded function is not continuous. So according to this one, linear transformation of n into n dash is continuous overall. Yeah, same theorem is also stated as every linear transformation is continuous with respect to, you must apply the particular norms, with respect to all the norms on the finite dimensional linear space. Okay, this is the end of this unit. Just you have to see and refer the another one. Fifth unit is here. That is dual of Banach space. Dual of Banach space. Okay. Now, particularly in this session, one essay or one short answer is given on every time in the final examination. Okay. So, according to the subject, now that duality is also one of the important concept. So, duality is also referred in the previous session is there. The set of all bounded continuous linear functions. Okay, that is called a duality. Now this is that is denoted by B of n and r. Say this one. The set of all continuous linear transformation of n into capital F. You are taking, suppose, students, suppose given this field, you are taking the real numbers, that is called a Euclidean space or real linear space. Okay. Now, so we are taking the field of the elements are complex numbers, that is also denoted by complex unitary complex vector space or complex inner product space and a unitary space. And through the real or complex and normal linear space, that is denoted by the set of all bounded linear continuous functions defined on the real numbers or complex numbers. That is called dual of linear space, that is denoted by n star. Okay, dual space is denoted by n star. In sometimes that is also called in the, suppose, in the inner product space of the concept, already we have explained in the under UG level, we have learned in the UG level in an inner product space, and star represent is called the, suppose complex analysis, just you have to see and refer. Complex analysis is also there. Z bar or Z star. Here n star is also, it read as conjugate space. What is that? This is n star is called a dual space or conjugate space. So the elements of n dash are called continuous linear functional. So dual space of the elements, it is also called continuous linear functionals. And it is more briefly, that is the functionals of the part, functionals of the element. These functionals are with respect to the addition and multiplication by scalar pointwise of their norms of a functional f defined by. Now here the condition is that this is one of the important condition. You must applying in an every theorem norm f equal to. Now this concept is also referred in a real analysis in MSc first year, previous paper, second paper, and according to this the conjugate, so that is the topological expression is also there. So here the norm of the functional is supremum of mod f of x. So don't forget this one. Through the linear functional, we are taking the in the dual space functional part is norm with respect to the pointwise norm is defined by norm f equal to. Okay, suppose in examination it is given in an indirect part, define dual linear functional norm. So that is simple expression is here FB any dual functional. So that is norm f equal to supremum of mod f of x. So according to this expression is denoted by n star. Then automatically through when you must applying given this defined part, norm f equal to supremum mod f of x, norm x less than or equal to 1. This is the main important condition through the norm of the duality part. So here n star, that is the conjugate of Banach conjugate or dual space. Conjugate space or dual space is also a Banach space. Students, please stay on the line. Please stay on the line. Please stay on the line. Okay. Hello? Can you hear me? So, yeah, please see this theorem. Let N be a finite dimensional normal linear space. Let N be a finite dimensional normal linear space over a scalar field capital F, then every linear functional on capital N is bounded. So, first of all, what is the connective mapping? Here, n varies from begin the linear functional capital N is bounded. The dual space is n star is also finite dimensional. Here, at the same time, now linear functional and a dual space n star or conjugate space n and n star both are finite dimensional, have the same dimension. So, domain of the linear functional and the codomain of the dual of the part, both are finite dimensional, have the same dimension is there. This is one of the theorem through on dual space part. Suppose we are taking capital N is n dimensional. Just see and observe this theorem. See and observe. Please stay on the line. Okay. Suppose given the dual of the part, okay, suppose that n is n dimensional and we are taking in any n basis of the part, here E1, E2, so on, En. Now E is also represented as the standard basis or usual basis or regular basis. Okay. Now, sometimes here E1 means on the n dimensional part is 1, 0, 0, so on 0. E2 is 0, 1, 0, so on 0. And En is 0, 0, so on 1. So this is called usual basis or regular basis or standard basis. Now all the standard bases are always on n dimensional part linearly independent, because when the linearly independent, now then automatically all the elements must be generated here. So that is also a linear span. Standard bases are linearly independent. Now you are taking, given the finite dimensional elements in the domain E1, E2, so on, En on n dimensional part. So that is the basis for n. Now it is uniquely formed. You must applying with respect to all the elements on the n dimensional of the basis elements. You must write the linear combination, that is x equal to summation alpha I and ei. So alpha I means that is the field elements, alpha 1, alpha 2, so on, alpha n. Now it is easily that the function, now x be the x, then the norm is norm x equal to summation mod alpha I. So it is also a norm on n. Any two norms on a finite dimensional space are equivalent. Already we have proved this, the theorem is also here. Any two finite dimensionals are, any two norms on finite dimensional are equivalent. You must applying the theorem 4.3.7 is there. And according to that, there exists here one of the positive real constant, that is norm x at 1. First norm of the norm x is less than or equal to m into norm x. Now, according to that theorem, then you must, you are taking the one of the condition is norm x at 1 less than or equal to m into norm x. Here, I varies from 1 to n representations. That's why fi of x equal to alpha I. So, for all x being the n values, so x can also be written as summation alpha I and ei. That is the linear combination for the linear functional on n, now absolute of fi of x. So you are applying the both sides of the absoluteness. My absolute of fi of x equal to mod alpha I and less than or equal to summation alpha I. So norm x at 1 less than or equal to m into norm x. Now, here the fi is also dual of the space. Fi is also consisting dual part. So here I varies from all the function values. Here all the function values means that is the image of the expression n to n dash. So here n, we are taking the n dash is n star. That is the dual of the part. The set of all continuous linear functional elements, that is called dual space. Okay. That is capital B of n to R or capital B from n to C. So that is the dual space. We are taking the image of the element, the image of the linear functional fi is also consisting n star. So here I varies from 1 to n representations. So the set of all linear functionals is always linearly independent, because we are taking the, given the set of the elements are standard basis. Already we know that, already we have learned all the standard basis, all the regular basis, all the usual basis are always linearly independent. That's why that is the basis for basis on linear functional. So there, that's why please excuse me. The set of f1, f2, so on fn is linearly independent. So our assumption, we are taking another one on linear functional of the scalar summation beta I and fi equal to 0. All the beta I elements are field elements because that is a scalar. So that is the that linear combination must be equal to 0. 0 equal to summation beta I and alpha I with respect to ej. Okay. Summation beta I and fi of ej equal to, now that is also denoted by beta j. Enter this expression is with respect to the standard basis is also consisting that value say beta j. So that is the orthogonal or the orthonormal. Now according to the orthonormal condition, if it is j equal to I equal to j, that value is 1. this value I equal to j, that value enter this value is an equivalent to 1. Suppose I not equal to j, that value is 0. So that is the orthogonal element. So I equal to j, so we are taking the unit vector, and I not equal to j, so that linear combination of the part summation beta I and fi with respect to ej means the usual basis elements, that value is say beta j. So how to define the beta j value? Suppose I equal to j, so fi of ej equal to 1. Suppose I not equal to j, fi of ej equal to 0. So at the same time, beta is j equal to 0, j equal to 1 to so on, and this shows that the linear functional of the set are linearly independent. Finally, now after the, if it is basis, now you must prove that that dual space must be generated. Generated means spans. Students, listen carefully. Now, what is the basis of linear space? Given the any subset of vectors, is it a basis of basis for a vector space? Basis of a vector space or linear space. First condition is given the subset S is linearly independent, and second one L of S equal to V means L of S means linear span. So linear spans, the generated vector space is also a linear space elements. So that's why the dual space must be a spans on linear functional elements. So F can also be written as summation lambda I and Fi, and again it can also be written as a dual of the part in terms of lambda values of the functional representation. So lambda I is F of Ei is there. Here I varies from 1 to n. So that's why we are taking the linear space element is x, and enter this vector stated as, already we know that x equal to summation alpha and ei. So applying on both sides functional part, f of x equal to f of summation alpha I and ei. So that can also be written as summation alpha. Alpha means that is the scalar. So alpha I into f of ei. So f of ei represented as lambda I. F of ei represented as lambda I. So that's why lambda summation lambda I into fi of x by definition of f1. Fi definition means fi means that is a simple representation is fi of x, because lambda I equal to f of ei. So summation lambda I into this expression is lambda I fi with respect to x for all x belongs to n. So enter that value is f equal to summation lambda I and fi. So lambda I equal to f of ei. So that's why here the linear functional dual space or conjugate space is also finite dimensional, and the what is the dimension? That dimension is n, because it is consisting n basis of the elements, n basis of vectors. So that's why here the dimension is n. Okay. So prove that n star is finite dimensional and find the dimension. So dimension is n. So dual space is also finite dimensional. You must applying given this proof, that is the 5.3.1. This theorem is very important. If n is dimensional, if n is finite dimensional, prove that dual space is also a finite dimensional. So then the theorem is 5.3, because n and n star normal linear finite dimensional normal linear space and a dual space of the finite dimensional normal linear space, both have the same dimension. This theorem is also very important on dimensional region. Now let us see this one. Just you have to observe given this remark. From the above theorem, it follows the previous part in the fourth unit of the sixth theorem is a n dimensional of linear space. N dimensional of linear space is, that is called Euclidean space. Dual space of Euclidean space or dual space of n dimensional of real linear space is also r power n. Duality of this one r power n can also be represented as LP at 1. N dimensional on LP. It read as n dimensional of LP. Okay. that is the LP means that is the linear space on the dimension is n. That is the also represent LP. N of the conjugate is also equivalent to LQ at n. N dimensional all on LQ. So here P lies between 1 to infinite. So that is one. Here the condition is how to derive the dual of LP at n equal to LQN. Or this canal or R power n means n dimensional of real linear space conjugate or dual of n dimensional of real linear space equal to n dimensional of real linear space. That is also called Euclidean space. So the dual of Euclidean space is also Euclidean space. The dual of LP space on n dimensional equal to LQ of the n dimensional. So here the condition is Holder inequality. From the Holder inequality 1 by P plus 1 by Q equal to 1. So this is, see this theorem 5.3.2. This theorem is also important on duality of the sequences of the converges to 0. Now what is the C naught? See this theorem, each and every one connectivity with from another second part. C naught be the, it denotes the linear subspace with constants of all the sequences that converges to 0. C naught means, what is the C naught? Define C naught means the linear subspace with the constants of all the sequences. Constant of all the sequence converges point is 0. So the dual of linear subspace with which constants of all sequences equal to L1. So the dual of C naught equal to L1. Don't forget this one. What is the C naught? The linear subspace which consists the linear subspace which, sorry, it is not the linear subspace which consists of all the sequences. If all the sequences that converges to 0. So linear subspaces of all the sequences converges to 0 means the dual of C naught equal to the dual of linear subspaces which consists of all subsequences, which all sequences which converges to 0 of the dual is L1. First of all, how to prove this one? This is the Kronecker delta. This representation read as Kronecker delta is mm. Kronecker delta is del mn, not mm is here. This is mn. So Kronecker delta of del mn equal to 1 if m equal to n is here. Suppose m not equal to n, that value is 0. Okay. Suppose you are taking the m varies from 1 to so on. So Cn can En means that is the n dimensional of the standard basis represented as in the Kronecker delta representation, del 1n, del 2n, so on, so on. And En means what is the En? N dimension of the part 0, 0, 0 and the nth place representation is 1. This is nth place. Suppose beyond that of the nth place, remaining all the values are 0. Okay, because En means that is the one of the standard bases in the nth place is taking that value is 1. The remaining all the ordinates are 0. So En equal to set of 0, 0, so on 1, and then after that all the values are 0. But here nth place you must be denoted in the you are taking the value is 1 in on nth place. So x equal to set of alpha I. It is also belongs to C naught. And what is the Sn? Summation alpha I and Ei. Because now set of alpha I values is consisting X representation in the subsets, the linear subspace which consists of all the sequences converges to 0, that is denoted by C naught. So you are taking that, given that subspace of the sequence, so that is, that value is X. Say X is here. X equal to set of alpha I. Now that is also consisting C naught. So X belongs to C naught. Now, and according to this one, you must write the summation of the value, summation alpha Ei is say Sn. So the difference between X and Sn, so norm X minus Sn equal to, and this is the functional part. Say this is F. Now what is the norm F? At infinite. Norm f at infinite means supremum of mod f. Already that definition is also defined through the dual of the space, linear on linear functional part. So norm x minus Sn at infinite equal to supremum of mod alpha I varies from n plus 1, n plus 2 and so on representations. Because up to infinitive representation, already nth place is also you are taking that value is 1. So that's why since alpha I converges to 0, it follows that norm x minus Sn is less than epsilon. Epsilon is always greater than 0. So that's why, and according to this one, there exists a positive integer is capital M. Positive integer is capital M. So what about the condition in n in between n and m? N is always greater than or equal to capital M is here. And f belongs to dual of C naught and beta n equal to f of En. So that representation can also be stated as absolute of f of x minus a summation alpha I and beta I. Summation equal to mod f of x minus summation alpha I, and you are taking the replacing the value beta I means f of ei. So f is common and that expression is x minus summation ai and ei. Now that value is absolute of f of x minus this value is say del n. So absolute of f of x means norm f is less than epsilon into that value is less than epsilon into norm f into norm f into norm x minus del n. So here n is always greater than or equal to m because f of x equal to summation alpha I and beta I is here. So sequence of beta n sequence is also belongs to L1 because that is the functional representation of the part on the dual space. Say this is L1. Now here what is the value of lambda I? Lambda I, when you must define the lambda I, that value is 0, beta is equal to 0. So lambda equal to norm beta mod beta I by beta I. If a beta I not equal to 0. Okay. Here xn equal to summation lambda I and ei. Then it follows that norm xn at infinite is less than or equal to 1. And you have to apply the f of xn equal to apply the linear functional because this is the dimensional dual of the part. F of xn equal to f of lambda summation lambda I ei. Summation lambda I into that can also be written as f of ei. F of ei means beta I. So enter that value stated as lambda and beta I means mod beta I is here. So finally summation beta I equal to mod f of xn. Mod m means norm f into norm xn. That can also be written as less than or equal to norm f. Here norm xn is less than or equal to 1. That condition is given. So summation beta I is less than or equal to norm f. Summation beta I is also belongs to L1. Already this is the linear space of the first linear space. T defined the map that is the dual of C naught approaches to L1. So the connectivity of dual of C naught approaches to L1 to define the transformation is capital T. So T at F, TF equal to sequence of beta n. You are applying the norm on both sides. Norm TF equal to norm sequence beta n. Now again, you must write the beta n value summation beta I, absolute of beta I. You enter that value less than or equal to norm f is there. So finally norm Tj, Tf equal to norm f. So that is the identity. So because I of x equal to x, at the same time on the transformation, norm Tf equal to norm f is there. So definition of transformation, it is easy to verify that given that transformation is 1 to 1 and linear is there. And again, we show that capital T is onto. Onto representation means given the sequential part, sequential value in C naught is here, summation alpha I, beta I is also converges absolutely. When the absoluteness, when you must apply the absoluteness of the convergence, again, you must write the f of x equal to summation alpha I and beta I. So given the function is bounded and linear on C0. Hence it follows that the dual of C0 of the linear functional is f, say f of en equal to beta n. So that is on to part. So summation, when already we know that summation alpha beta converges absolutely, and according to that condition, norm f of x less than or equal to summation mod beta I. So norm x at infinite, linear space of the dimension when it is infinite. So norm x at infinite less than or equal to 1. So simply it is stated as norm f is equal to norm tf. So finally, A contained are equal to B, and induction concept, through induction concept, norm tf equal to norm f. So when it is 1 to 1 and continuous linear and bounded of the part, norm tf equal to norm f, T is an isometric isomorphism of C0, the dual of C0 onto L1. So finally, hence, the dual of C0 approaches to L1. Simply in examination, prove that T is an isometric isomorphism of C0, the dual of C0 onto L1, or the dual of C0 converges to L1. So that is the proof of given this theorem. Okay, that is very simple. In the same manner, you must see and write here, and on the same, you are using with the standard basis of the part, the dual of L1 equal to, already L1 is also a codomain of the part, because convergence point is L1 is here, and according to the continuity of a dual of L1 equal to L2, and dual of L2 equal to L3, and so on. In the same manner, the dual of L1 equal to L infinite. This is also important, and you must practice in the above theorem. That is also in the same manner. There is no deviation here. Okay. L1 star equal to L infinitive. Now these theorems are very, very important, especially in this unit, that is the dual of Banach spaces. Now that is one essay is given and one short answer is given in this unit. So students, much more possibilities. You must qualify and you must get in the good marks in the, especially in the functional analysis paper. Okay. L1 star equal to L infinite. This theorem is also in the same manner of the above theorem. Okay. T is 1 to isometrical isomorphism. Okay. This is T is an isometric isomorphism of L1 star onto L infinite. So in the examination, prove that L1 star equal to L infinitive. Star means it read as the dual of L1 equal to L1. Conjugate of L1 equal to L infinite. Okay. Now this theorem is important. 5.4. Just you have to, what is the LP spaces? See here. What is the P? The base value of P, hence the condition of LP dual is dual of LP. What is the dual of LP? Here the condition is P lies between 1 to infinity. This is the particularly infinite interval of this part. So P is greater than 1, but it is less than infinite. So 1 less than P less than infinite theorem. Just you have to see and rectify this theorem. If P is greater than 1, LP star equal to LQ. The conjugate of LP equal to LQ. When here the particularly given the condition is P is greater than 1. Hence the Polar inequality condition is 1 by P plus 1 by Q equal to 1. And the difference between the relation between P and Q is here. 1 by P plus 1 by Q equal to 1. So that is P is isomer, then the conjugate of, it read as conjugate of LP is isometrically isomorphic to LQ. Suppose examination is given either this one or this one, simply. Okay, there is no doubt. This theorem is also very important, and these are also consisting in measure and integration and operator theory paper. Please, you must understood each and every word throughout my delivered words. Okay. En equal to, what is the En? Nth place is 1, and that is the standard basis of nth place is 1 and the remaining are 0. So here 1 is in the nth place and 0 in another components. That is the meaning of this one. And yeah, standard basis of their norm is 1 because each and every one is 0 and nth place is 1. So that's why we are getting the norm En equal to 1 is here and n equal to 1, n equal to 2, whatever it is. And x equal to set of alpha n. Already this is one of the sequence. That sequence is say L from the beginning of dual concept in LP. So Sn is also, you must same manner. And you must explain the Sn equal to summation alpha and Ei. Here I varies from 1 to n is there. So to express the norm relation in between x and Sn is there. Norm x minus Sn equal to summation 1 to infinite mod alpha I whole power p and whole power 1 by p on, okay. So this value is converges for each epsilon greater than 0, and the norm x minus Sn is less than epsilon. So we are taking the linear functional on dimensional, that is the conjugate of LP. We are taking the linear functional is f. The dual of LP is, say, one of the linear functional is f. So that can also be written as an equal to, what is the an? F of en. Here n equal to 1, a1 equal to f of e1, n equal to 2, a2 equal to f of e2. So mapping is defined from T defined the dual of LP to LQ. So what about the relation? We are taking the any linear function, let's say f. So T of f equal to, what is the value of LQ? LQ value is the sequence of an is here because this is the LQ representation. That's why we are taking the when we must applying the functional part f of x equal to summation alpha I and ai. So the absolute of f of replacing x by x minus Sn less than or equal to this value already is practiced here. Norm f into epsilon, because enter this value, say epsilon is here. So absolute of f of x minus Sn equal to f of x minus f of Sn. And f of x minus applying the f of Sn value summation ai into, just you have to see and observe in the above expression, f of norm f into this value summation mod alpha I at on whole power p, because norm means square root of pth root of p square. Okay, the square of p. The summation mod alpha I whole power p and whole power 1 by p, because p lies between 1 and epsilon. So norm f into this value, say epsilon is here. So mod f of x minus Sn equal to f of x minus f of Sn. So this is f of x minus, this value is again summation alpha I and f of ei. F of ei means ai is here, replacing of that value is ai. So f of x minus summation alpha I ei equal to absolute of f of x minus this value is Sn less than epsilon into this value can also be cannot exceed the epsilon into norm f for large values. Finally, f of x equal to summation alpha I ei. So you are taking the sequence an. Already we now show that sequence an is in LQ. An sequence is already in LQ is there. That is the image of the linear. So beta I equal to absolute of ai and whole power q minus 2 ai, because here ai not equal to 0. Suppose ai equal to 0, that value is 0. So here xn equal to summation beta I and ei. Then clearly xn belongs to LP for all n values. Further, we find f of xn equal to summation beta I and f of ei. Summation beta I and f of ei means ai. Now again that value summation mod ai whole power q. Summation, what is the value of this one? Absolute of f of xn. It cannot exceed the norm f into norm xn. So norm xn means summation beta I whole power p and whole power 1 by p. And according to the inequality, so that can also be stated as mod beta I expression is mod ai and whole power q minus 1. Because we know that 1 by p plus 1 by q equal to 1. And replacing the value of, what is the value of p? we have 1 by P equal to 1 minus 1 by Q. 1 minus 1 by Q means Q minus 1 by Q. Okay. Q minus 1 by Q. So P equal to Q by Q minus 1. Okay. So P by Q minus 1 is there. So from the inequality of this unit, from the first theorem, summation mod AI whole power Q less than or equal to norm F into, this is the expression summation mod alpha mod AI whole power Q and whole power 1 by P. Because enter this value is less than or equal to cannot exceeds. So dividing of this part, enter that value is dividing given this one. So we are getting enter that value less than or equal to norm F is here. So norm TF is greater than or equal to norm F. So already we know that norm F less than or equal to norm TF. From the first and second equation, here F belongs to conjugate of LP or conjugate space. So in LQ, you are taking any one of the sequence, define the linear functional f of En equal to An. That is the relation of LQ. So x means x1, x2, so on, xn. Okay. So that is also belongs to LP. So finally, f of x equal to summation Ai and xi. Summation mod f of x less than or equal to summation Ai xi less than or equal to norm Ai into norm x. By Holder inequality already I told here. Okay. Now in this inequality, Holder inequality, according to Holder inequality, we must express mod f of x less than or equal to norm Ai into norm x. So linear function is bounded given the mapping is onto. So finally norm f less than or equal to norm of Ai sequence. Norm of Ai sequence means simply that is TF is there. From the second and third equation in this theorem, norm TF equal to norm F. So T is linear map from the dual of LP onto LQ. So that is the simple expression. So finally the dual of LP is isometrically isomorphic to LQ. That is the given the statement derived here. So finally the dual of LP equal to LQ. The dual of LP equal to LQ means isometrical isomorphism. So that is the first of all, when you must equal the one to one of the part and continuous of the bounded. Okay. Now just you have to practice these theorems. Dual of C of AB. C of AB means the set of all continuous functions on closed interval AB. Okay. So here already you have to practice the dual of already we have derived the theorem is in the previous theorem, the dual of LP equal to LQ when the P lies between 1 to infinite, as the Holder condition, Holder inequality condition is 1 by P plus 1 by Q equal to 1. So the dual of LP equal to LQ, this is also true, hence the condition when the condition P equal to 1, theorem is obvious. Suppose P equal to infinite, so the dual of L infinity equal to L1. That is not true here. So suppose in the short answer is given according to given this, just you have to observation. Okay. Derive, prove that LP star equal to LQ. LP star equal to LQ. If a P equal to 1, is it true? And also applying the case at P equal to infinite. How to justify? So the dual of L infinity equal to L1 is not true. So the dual of C not equal to L1 and C naught is the special subspace of L infinite. Okay, that's enough. What is the C of X? The space of all bounded continuous real valued functions defined on the topological space. The norm is, what is the norm F? Supremum of mod F of X. See this one. This is very, very important. The linear operators. Okay. This is the, according to this one, this is one of the classical solution for this problem of the space X, which is compact and Hausdorff. Compact Hausdorff is known as Ries representation theorem. Okay. And this theorem is also given the theory of measure integration. This is also repeated in the measure integration here. And at the same time, operator theory paper is also consisting of this part. Okay. Now replacing capital X by closed interval AB on the real line. So this is the space of functions. The space of functions BB means bounded variation on closed interval AB. The space of bounded variation on closed interval AB. Already bounded variation concept is was introduced in a real analysis paper, and continuous function is bounded variation, and at the same time monotonic function is also bounded variation. And according to that concept, Riemann-Stieltjes integrals, continuous function is RS integrable, and at the same time monotonic function is also, when the function is monotonically increasing or decreasing, that is also RS integrable. So you must observing, given the any bounded variable function is, say g is there. Here what is the g means? G of x. Here with respect to x means x is consisting of interval. So that is denoted by Vg of x. What is the meaning of Vg of x? This is the total variation of G onto closed interval A and X. Total, this is also representation, total variation of G on closed interval A comma X. So Vg of B equal to V of G. V of G means the total variation of G. So by the representation theorem, the dual of the C of AB identified the subspace of bounded variation of interval AB. This is the functions of bounded variation. Already we have discussed in the Riemann-Stieltjes integrals concept. Previous, just within a few minutes back, I was explained here. One is connectivity, bounded variation, and RS integrable one is connected to another one. Okay. So simply that is capital F of, capital F means bounded linear functional defined on small f equal to f of f equal to bounded linear functional defined on f equal to integral, because this is the Riemann integral concept, integral a to b f dg, because f is consisting of what is the C of AB? The set of all linear functionals defined on closed interval AB. Okay. Now, f of f equal to integral a to b f dg. Okay, here g is also one of the linear functional. So, that function is linear. So, in f belongs to C of ab, and g is also bounded variation on interval ab. So, when the normal linear space, when you must applying the normal linear space, norm g can also be written as total variation v of g plus mod g of x. That is the definition of norm g. With respect to the constant of the part. So integral a to b f dg cannot exceed the supremum. The f means that is also you are taking the supremum of mod f of x. That's why supremum of this value is also supremum of mod f of x into v of g. Here x lies between a and b. That is the closed interval a b. So finally, G is also, every element G is also bounded variation on interval AB, and it determines bounded linear functional F on C of interval AB. By the formula, you must applying given this expression in the further theorems. F of f equal to integral a to b f dg. Here f is also consisting of C of interval AB, and norm f equal is less than or equal to total variation, that is V of G. So that is the unique function is also here, g equal to g star, and at the same time integral of right continuous and left continuous is also here. Integral a to b f dg equal to integral a to b f dg bar. So total variation on g, so vg bar is less than or equal to v of g is here. Here g bar means that is the existence of the unique function. Existence of the unique function on bounded variation g equal to g bar is here. That is the unique of this part. Okay. Finally, g converges to integral a to b f dg on the total from the total variation of this part. So that is also represented norm decreasing transformation of bounded variation on normed closed interval ab into conjugate of C of ab. So f is also consisting, C of AB is 1, 1, linear, norm decreasing transformation of bounded variation on closed interval AB means normalized functions of bounded variation. Normalized functions on bounded variation means BVN of AB. Now that is the representation of normal linear bounded variation functions. Okay, and according to this theorem is also very important. These theorems are integration by parts, fundamental theorem of integral calculus. These theorems are referred in algebraic part is there. But in the particularly throughout the bounded variation and Riemann-Stieltjes integrals, you are taking the conjugate of C of AB function is capital F. There exists a small b is the normalized bounded variation function on closed interval AB, small g, and f of f equal to integral a to b f dg. F is consisting C of AB, norm g means v of g minus v of g. Norm g equal to norm capital F. So that value is a bounded variation. So you must apply given this condition. This theorem is very important. Please see and referred here. Okay. This theorem is also important. And according to this one, here M of closed interval AB means it denotes the space of all bounded functions on closed interval AB. That is the with the supremum norm. Okay. And easily to see that C of interval AB is a subspace of M of AB. And norm F, we know that norm F can be extended to capital M of closed interval AB. So norm F less than or equal to V of G equal to norm G. So we consider the following inequalities: pi x of t equal to 1. Here t represented in between a and x, and the continuity of the interval is x less than t less than or equal to b. So you are taking in any one of the element is x is consisting in between a and b. So t is lies between a and x. That is the integral defined part t with respect to t. So t is consisting a to x, that value is 1. So that is the pi of xt. We are taking the integral value is 1. And another integral value, t lies between, that is the semi-closed interval, x to b, that value is 0. So pi in a of t equal to 0 if t lies between a and b. So g of x equal to capital F of pi x. Here x is consisting of closed interval ab here. So how to calculate, how to compute the value of P of G total variation? So here the consisting of values in between A and B. So that is that those values are consisting of X is here. These are called X0, X1, so on Xn. Okay. So these are all partitioned points. This is called x consisting of the partitioned points of x, x0, x1, x2, so on, xn minus 1. And in between rth subinterval is also there. xr minus 1, xr, and so on, xn minus 1 and xn. So in between of this, is you are taking the one of the real line is here. Already this is for Riemann-Stieltjes integrals concept. Now closed interval AB means you must consisting of the element is x. So x is lies between A and B. So all the elements of x lies between A and B is here. A equal to x0 and terminal value B equal to xn is here. That is the initial value and terminal value. So that is summation mod g of xi minus g of xi minus 1. Here I varies from 1 to n. Summation, that is set of g of xi minus g of xi minus 1 and signature functions. Now here signature function is g of xi minus g of xi minus 1. Okay. Now this expression is denoted by this value is pi of xi, this value is pi of xi minus pi of I minus 1, and signature function is that is g of xi minus g of xi minus 1. Enter that value applying the norm, and according to that, that value is norm f. So v of g total variation on g is less than or equal to norm f is there. Finally, now this is the converges uniformly part. Now that's why f of f equal to integral a to b f dg. G is also taking the one of the bounded variation on interval AB is here. So finally, this is G bar is also consisting normalized bounded variation function, and f of f equal to replacing G by G bar. Now both are equal. G, when G equal to G bar, that is the uniqueness of the part. So the conjugate of the set of all continuous functions on interval AB is one function is capital F, and G bar is also existing of the normalized bounded variation function on interval AB. So finally, f of f equal to integral a to b f dg. So both are equivalent is here. So here G equal to G bar is unique. That is the simple concept. Okay, this is the end of this unit. And just you have to see and refer, that is the 6th unit is here. Hahn-Banach theorem. This theorem is very, very, very important in the university examination. And before that, Hahn-Banach means Hahn is also one of the mathematician. Banach is also another mathematician. So both concepts are a little bit defined part. Both concepts are same. In between Hahn and Banach is there. So the theorem is called Hahn-Banach theorem on linear. Throughout this theorem is defined on linear functional part. Okay, don't forget this one. Now, according to the previous unit is also connectivity of in this unit especially, because Hahn-Banach concept is norm f equal to norm f naught equals to norm f, and in the suppose norm g equal to norm g bar equal to norm g is there, and throughout the linear function of this part Hahn-Banach theorem concept, and before the just you have to see and refer the John lemma, and before the John lemma well ordering principle and partial order set. Okay, now this is the important concept. Students, listen carefully. This is one of the important theorem. Please stay on the line. See this theorem, John theorem, Hahn-Banach theorem, and before the concept of John lemma, and before that, here, what is the, hello? Sir, is there any problem, sir? Okay. First of all, sir, if you have any objection, students, listen carefully. Now, this is the partial order relation is denoted by less than or equal to. Okay. This is the partial order relation, that is less than or equal to of the part, and symbolically it represents the partial order relation denoted by less than or equal to and satisfying all the properties throughout the non-empty set. So any partial order relation denoted by less than or equal to and throughout the order relation, you must satisfying throughout the and with respect to the non-empty set of the elements is a relation is called partial order relation. So that is the one is the reflexive. Now these theorems are also practiced in the previous part DMS paper. Okay. Now each and every one is important here because without partial order relation and under UC level, well-ordering principle, mathematical induction and well-ordering principle and those basic properties are also we must applying in the so many theorems. But here, particularly here, the one of the partial order relation is denoted by less than or equal to, and given the non-empty set elements are denoted by capital S. Here, x less than or equal to x. Here, x less than or equal to x means for every small x belongs to capital X. That is the reflexive part. So x is on x. And second one, anti-symmetry. X is on y and y is on x. Suppose x equal to y is there. That is the anti-symmetry property. And next one, x is y and y is on z. And that is also x is on z is there. That is the transitivity of the part. Now, when the reflexive, anti-symmetry and transitivity, when these three are satisfied, okay. Now, partial ordered set means throughout the partial order relation, you must satisfying these three properties, reflexive, anti-symmetry, and transitivity. When these three are satisfied, that is called partial order relation. Okay, a partial ordered set, any two elements are comparable. Suppose in the partial ordered set, you are taking any two elements. Now, these are also very important. Any two elements given in the partial order set, that is x and y, both elements are comparable. That is x less than or equal to y or y less than or equal to x. That is called comparable. Comparable means if in the partial ordered set elements x and y belongs to capital X, here capital X is the partial order set, and before that, now here X be any non-empty set using with the help with the part of partial order relation, and the following conditions are satisfied: reflexive, anti-symmetry, and transitivity. When these are when these conditions are satisfied, properties are satisfied, that is called a partial order relation. Okay. Now, according to this one, those elements are comparable if either x less than or equal to y or y less than or equal to x. So, a partial ordered set in which any two elements are comparable. Any two elements are comparable. Okay, is called a totally ordered set or a chain or a linearly ordered set. So, define a chain or totally ordered set means any two elements are comparable. Comparable means any two elements, that is x less than or equal to y, y less than or equal to x. Here x and y be the partial ordered set elements. Now those elements on the partial ordered set, x is on y, y is on x, that is called comparable. And comparable of the elements, any two elements are comparable, that is called a chain, totally ordered set or linearly ordered set. So an element x be the one of the element in a partial order set, that is called maximal. What is the maximal condition? When the condition is y less than or equal to x implies that y equal to x. Okay. Now, and according to this one, what is the lower bound and upper bound? Here we are taking any two elements, x less than or equal to a or a greater than or equal to x. Here, A small a being the one of the non-empty subset element. So, any subset element small s less than h and k being the field of the element. Suppose, just you have to see and observe here. Just you have to draw be one of the real line. Draw the one of the real line. On the real line, h and k be the initial and terminal final values. Okay. And S be the subset is there. Subset of the element is say small s. Small s less than or equal to k. K be an upper bound of S. And H be the lower bound. That is small s greater than or equal to H. Here greater than representation. Subset element is greater than or equal to field element. So that is called a lower bound. Particularly here, okay, lower bound and upper bound is there. Bounded below, aggregate of the bounded below is called lower bound, and aggregate of the bounded above is called an upper bound is here. Okay. Now a lower bound of capital A is called greatest lower bound of capital A if it is greater than or equal to every lower bound of capital A. So, that is the difference between the infimum and supremum. Greatest lower bound is called. So, subset of the lower bound is called greatest lower bound. Is it that is greater than or equal to every lower bound of the subset. So, here x being the element is y. Y belongs to x is called an upper bound of capital A and small a less than or equal to y. For every small a belongs to capital A. So, an upper bound of A is called the least upper bound. So, that is called the supremum, and upper bound of the value is equal to every upper bound of the subset. Okay. Now, this is one of the important example for partial ordered set. So, that is x less than or equal to y means y minus x greater than or equal to 0. So, because greater than or equal to 0 means that is the non-negative. This is one of the partial ordered set using with the set of real numbers. That is the script R. Script R means a set of real numbers is a partially ordered set. That is one of the example. So, is the greatest lower bound which is usually is called infimum. So, that is infimum of capital A. And non-empty subset A of R has an upper bound. So, least upper bound is called supremum. That is called, it is denoted by supremum, SUP of A. That is the basic part of real analysis. They enter the analyzation of this part. And another example of partial order relation, a class of all subsets, some universal set. Universal set is denoted by capital A and universal set is U, and class of all the subsets is capital X. So, class of the subsets in an universal set, that is also one of the relation. So, A, capital A and B, there are two subsets. A is a subset of capital B. It read as A is a universal set and class of the subset of the relation A less than or equal to B. This is also one of the partial ordered set. And with respect to the relation is less than or equal to, that is the partial order relation. And the third example is set of all real valued functions defined on a non-empty set, capital U. Here capital X is the real valued functions. So partial ordered set and give example means you must write the these three examples in an for partial ordered set. So F less than or equal to G. That is a set of real valued functions. So F means simply that is F of X, G means G of X. So F of X less than or equal to G of X is here. Students, these examples are very important, and please see the John lemma. And next class, we will explain the one of the important theorem, Hahn-Banach theorem. Okay. What is the John lemma? X is a partially ordered set in which every chain means totally ordered set or linearly ordered set, has an upper bound. So, every chain has an upper bound, every totally ordered set an upper bound through the partially ordered set. It contains a maximal element. It contains means at least one maximal element. So, this is also called John lemma. Now, this is also referred to in the basic concept of well-ordering principle. Any non-empty subset of a positive integer. Okay, any non-empty subset is an at least an upper bound is there. So, At least one element is there. Okay. And according to this one here, John means that is the superior of this part. Here, at least element is there. But here, especially John concept is there. John is also one of the mathematician. Now here, we are taking through the partial order set, we must assume any two elements are comparable is called a totally ordered set, and that totally ordered subset has an upper bound. In an upper bound, it contains a maximal element is there. So that lemma is called John lemma. Now, explain John lemma or explain partial order set and John lemma. That is the short answer. Give example. Each and everyone is here. Okay. Tomorrow, okay, students. If you have any doubts are here, can you please ask any doubt? Please watch in the YouTube and more times also here. Now this session is very important for your purpose. Now this is much more utilization. Utilize the concept, functional analysis, and any paper is there. You must thoroughly for your understood of the concept here. Okay. Now here this is one of the important theorem in functional analysis. Okay. To meet on next class here. If you have any doubt, please contact us personally through WhatsApp for subject point of view. Number of times I have given, my number is there. Please note down once again my number 9989476833. Okay. Please stay on the line. See this here. Thank you, one and all. This is one of the important session here. Please stay on the line. Okay, students. Now, already posted my mobile number for the subject point of view. Please contact us and personally through WhatsApp. There is no doubt, because only there are remaining sessions. There are two only next week, Saturday and Sunday, as in the same manner. Okay, 16th and maybe 15th. Yes, 15th and 16th. There are two classes here, and some other concepts are also delivered in this session on the behalf of next classes. Okay, Horn-Banach theorem. This is also one of the important theorem. Please note down. And first of all, what is the definition of linear functional part? That is 6.4.1. And according to this definition, okay, now you must explain the 6.4.2 theorem. Next class I must explain here. There is no doubt. And according to this theorem, and direct theorem is also explained here. 6.4.2, 6.4.3. These two theorems are well established. In further theorem is Horn-Banach theorem. That is, both theorems are lemmas in the above concept. And 6.4.4. This theorem is also very important in each and every one. Okay, Horn-Banach theorem is also consisting in this paper, especially in the functional analysis and operator theory paper. Okay, there is no doubt. Especially in this session, from Horn-Banach theorem is also each and every one important in operator theory paper is also. Okay, same proofs are also relevant to operator theory. Okay, please understood here. 6.4.4. This theorem is also very important. I must explain in the further session. Okay. Now these are all consequences of the Horn-Banach theorem. That is 6.5.1. Yeah. Okay. 6.5.1, 6.5.2. These two theorems are also depends upon the Horn-Banach theorem, and these three are consequences. Okay. Thank you. Thank you, one and all. Okay. Time is over. Okay. These three consequences are very important in the further session. Okay, wish you all the best and wish you good luck. Meet again on the next Saturday and Sunday, that is 15th and 16th classes. Thank you, one and all. Okay, wish you all the best and wish you good luck. Thank you. Thank you, sir.